All right, starting off, we are going to look at a reaction that requires this much energy. How many kilocalories are required? You do need to know this conversion. That is not going to be given to you. Make sure you write it down on a 3x5 card so you can make that conversion. It's very easy, but it does need to be done. Somebody open the door. Please put the magnet back in for me. Thanks. I'll stop right here and wait. So 1 calorie is equal to 4.184 joules. You'll need to do that, okay? So as you go through kilojoules to joules, there's 1,000 joules in 1 kilojoule. Then once you get to joules, there's 4.184 joules in a calorie, and this is a lowercase calorie, not a kilocalorie. And then there's 1,000 calories in a kilocalorie. You'll notice the 1,000 cancels, the calories cancel, joules cancel, kilojoules cancel, so I just have to go this divided by 4.184, and I've got my answer. Next one, same thing, except this time you're going to kilojoules instead of kilocalories, so you're going opposite. So kilocalories to calories, get rid of calories, put joules on top. Joules to kilojoules. Again, the 1,000 cancels out, and you get this. Okay, next one. This is something that you also need to know. It will not be given to you. For fat, you get 9 calories per gram. For protein, you get 4 calories per gram. For carbohydrates, you get 4 calories per gram. So 9 calories per gram, 4 and 4. So fat you get the most calories out of. Protein and carbohydrates are 4 calories. So when it asks how many calories are in that sandwich, you're going to take the fat times 9 plus the protein times 4 plus the carbohydrates times 4, and you're going to add it all up. Okay? Protein is 4 and carbohydrates are 4. Fat is 9. It's really easy if you've got that written down on your card or you've got it memorized. But if you don't, then it makes it hard. Can I what? Yep, you bet. Yep, I can do that too. So fat, 9 calories per gram. Protein and carbohydrates, 4 calories per gram. Okay, so if you can remember that, you got it. Yes, sir.
Well, so is there a way, so if you forget which way it is, can you do like up at the top problem and convert it to calories or grams or something?
Nope, you've got to know it. So if you don't know it, put it on your card. Okay? So you either memorize it or you write it down. So those are the ones that you need to have. Okay? And there's going to be more than one problem like that you're going to need to figure out. So you just take however many grams you've got of each one times by the calories per gram. That gives you calories. Then add all the calories up. So this is my fat. I took my fat grams times the 9 calories per gram that I get out of fat to get the calories for the fat. Then I did the grams times the 4 calories for protein, and the same for carbohydrates. I ended up with how many calories that sandwich would give me. Yeah. I would just go this times this plus, this times this plus, this times this.
Just the numbers and then it.
Yep. Yep. Way easy. Okay, next part. What term correctly describes a reaction in which the energy in the product, so the energy in the products is lower than the energy in the reactant? So that means I start here, I come up, and I end up lower. That's going to be exothermic because I've lost. If I end up higher, that's going to be endothermic. Okay, if you have to draw yourself a picture, do that. But don't let the easy points go away. Okay, next one. Consider you've got this reaction where this happens. What does this tell me? The negative 137. What does that tell me?
Exothermic.
Yeah, it's exothermic and it's on the product side, right? I'm getting it out. So I start here. I can still do the conversion for every one of these. I get this much energy. I can put it into the equation. It's just like saying plus 137 kilojoules on the product side, right? If it was a positive here, it would go on the reactant side. Okay, I'm just going to convert it. I can say it negative here, or I can say it was released. Either one of those mean the same thing. So I've sort of been redundant by putting the negative and saying released, but that helps you. Okay, any questions with this one? So they can give it to you out here, and you just need to know what side it goes on.
So negatives product, positive.
Negatives on the product side, positives on the reactant side, because I have to put it in, add it in. Okay, next one. We've got an activation curve here. You can't really see it, so I'm going to draw it in dark. Okay. At A, it wants to know what A is. From the reactants to the top of the curve, that's known as the activation energy. It's E of A. B, this distance here, is delta H. It's the change in energy. This one happens to be endothermic because I put energy in and ended up higher. This right here is my activated complex. At that point, I can go backwards or forwards. That's my point of decision. D, my products. E, my reactant energy. And it's the amount of energy I have. Sometimes they put potential energy here.
One is the activation.
Okay, any questions on this? There are a lot of these on the test. Okay, are we okay to move forward? Like I said, I'm going to put this up on the web, and you can move it fast or slow as you want to. Okay, going forward. This next part starts to talk about Lechatleir. Everything has to do with this equation right here. So remember I told you, if I'm increasing something, I'm making a pile, and it's going to go away from it. So if I'm increasing O2, it's going to go away from it towards my products. Okay, if I'm...
Which O2 it's talking about? Is it just like...
There's only one O2.
So it's the only one that's like separate.
We okay? Increase CO2, so I'd be putting more in right here. I have to go away from it across the arrow, so it goes backwards towards the reactant. Next one. Increasing C2H6. Again, I have to go across the arrow. So I'm putting it in, going across the arrow, it goes forward. Next one. Increasing H2. I would write these down. I would take and I would write it down on my scratch paper, and I would actually draw this out. Yes, ma'am.
So is the products always like on the right side of the arrow and the reactants as well?
These are my products, yep, and this is my reactant.
I found a way that you can know the axis a little bit more.
Okay.
Because like if you go like when you go up, it's gonna go up and over, and then if it's gonna go the other way, it's gonna go down and under.
Down is not always going to go down and under.
No, like if you push it to the product side, it's gonna go.
So let's keep going to see. I'm not sure that will work. Okay, so we were right here, H2O. So if I put it in here, it's got to shift away from it, so it goes this way. O2, now if I take it out, I'm going underneath. I got to go across the arrow to fill the hole, right? So it's going to go backwards, okay? CO2, if I make a hole here, I've got to fill the hole, so now I'm going to go forward to fill the hole, okay? Now on this one, if I make a hole at C2H6, I got to go backwards to fill the hole. You okay? These should be easy points as long as you've written down the equation and do what I'm doing. You got to follow the arrow. Okay, if I decrease this concentration, I got to pass over the arrow, got to pass over this center thing, so it's got to go forward. Got to fill the hole. Okay, is anybody having problems with this?
Wait, will you explain that just one more time?
So if I'm taking stuff out, put the arrow underneath, and feel like I've got to fill the hole. So I've got to cross the arrow to fill the hole. If I'm putting it in on top, like right here, if I'm putting it in on top, I'm making a pile on this side. I've got to distribute across the arrow. So I've got to spread it out across the arrow. So it's going to go forward. Does that make sense? Okay. So hopefully these will be easy points.
Is there a lot of them tests?
Okay, if you're not listening, you're actually missing some easy points. Okay, so hopefully if you've written the equation down and use your arrows, these should be easy points. Okay, unless you get messed up. Okay, next part here. Catalysts do what? Now you got to make sure that you say don't just accelerate the reaction, but they decrease the activation energy. They lower the curve. So when I have a curve like this, a catalyst would bring it like this. They'd lower the activation energy. Okay? When we write an expression for KEQ, remember it's products over reactants. And you put brackets around them, and you put their coefficient as their exponent. That's it. It can only include aqueous and gases. Those are only things it can include. Cannot include liquids or solids. Cannot include those. Okay? When you're looking at an equilibrium constant, if it is bigger than 1, so greater than 1, then it goes towards the products. I think I've got this backwards. So if KQ is less than 1, I do have this backwards. KQ is bigger than 1, I've got those backwards. Okay, so I'm going to erase that real quick. KEQ is less than 1. KEQ is bigger than 1. I was doing this last night when I was watching TV, so I got distracted. Okay? All right, so if it's bigger than 1, it heads towards the products. So that's this one. If it's less than 1, negative, then it goes towards the reactants. If it's equal to 1, the forward and backward reactions are equal. So when we did our water, moving our water back and forth, that's when the amount of water moving forward and backward was the same. So our reaction rates are the same. Okay. This bottom one right here, you should be able to take a KQ and write an equation. Remember, the top is the product, so it's going to go on the product side. The bottom is the reactant, it's going to go on the reactant side. If they have put in something besides A, B, C, and D, you should be able to see if there was a solid or liquid that didn't get put in the KQ that I need to add into the reaction. Okay, make sure you figure it out. And since it said gaseous, that's how I got the states. Okay, so that's where we get the states. So you should be able to write that. So just go backwards. So this is my product, so that's A, and the exponent was the coefficient, so 3B. This is my reactants on the bottom, so D and 3C. Because the coefficients become the exponents.
Wait, how come there's 2 3s? Wasn't there 5?
Right here?
Yeah.
Yeah, there is a 5, so that should be a 5. See, I was watching TV and didn't have my glasses on, so that looked like a 3 to me. Good catch. Okay, we okay to go forward?
I don't know if I'm getting it.
Okay. All right, so looking at this next one again. Given the reaction this, what happens to the equilibrium when? And it talks about pressure. So the first thing I know I need to do is I need to find out how many moles of gas are on either side. So here I have 1 plus 2 equals 3. On this side I just have 1. So I have 3 and 1. So the pressure is increased. Whenever it's increased, it's going to go to the side that has the least amount of gas. Well, that's the product. So it's going to go forward to the products. If I decrease the pressure, it's going to go to the side that has the most moles of gas. So it's going to go towards the reactants. Okay? Fairly simple again, as long as you know what you're doing. Okay? She likes to do this visual stuff. Okay, so the molecular art depicts the following reversible reaction. 2A plus B goes forward to A2B. What can be inferred about the equilibrium constant? Yes.
For 13, you said the moles, when they're increased, go into the reactants.
So pressure is increased. It'll force it to the side that has the least amount of moles.
Okay.
Okay, if pressure is decreased, it'll go to the side that has the most. So on this one, you have to sort of look and say, okay, I have two products here, and I have 1, 2, 3 that are B, and I have 1, 2, 3, 4, 5 that are A. Okay, so I was just sort of looking at it and say, okay, well, I could have made more A to B, right? Because I've got enough stuff to do it, but it didn't. So it probably means that my reaction lies more to my reactants than it does to my products. Therefore, KEQ needs to be less than 1, meaning it's not a very favorable forward reaction because I didn't make all of that I could. It stopped. So it's going to be less than 1. Does it make sense?
So if there's not enough, then it's going to be less than 1?
So if all of them went to the product, then it's going to be very high, and I'm going to have a KEQ greater than 1. If I have the same amount of reactant and product, and it's going back and forth, then I'm going to be equal to 1. Now, it's going to be hard to show because equal to 1 just means that my ratio, my amount going forward and backwards is going to be the same. So she's probably not going to put one like that on there. Yes?
So if there was like leftover squares instead of triangles, would it be KEQ is greater than 1?
So B is the one I only need 1 of. A's I need 2 of.
Or what if there was like less B's than triangles, but like a lot less?
But the K just tells me, am I going totally forward and all I'm going to have left is this? Or am I going to go totally backwards? So this would be KEQ is bigger than 1. Or am I going to go mostly backwards and have more A and B than I have A to B? Okay, this says KEQ is less than 1. When I have more of the singles than I do of the compound. Okay? It means it takes a lot of energy to get it to go forward, so it's not very favorable. Okay? All right, so let's look at the next one down here. This is a reversible reaction. It has a K of this. That tells me right away what's happening. I don't even have to look at the equation because she starts now, instead of using symbols, she starts actually drawing out the molecular formulas. So this K right here tells me what? Just from what we just did up above. Which way is it going to lie?
Towards the product.
Towards the reactants. It's less than 1. If it's less than 1, it goes towards the reactants. If it's more than 1, towards the products. So I'm going to have more reactants than products. Okay? Based on the molecular art, what can be inferred about the reaction conditions? So here I have 1, 2, 3 of these. I have 1, 2, 3, 4 of these, and I have 1 of those. So I have more reactants than products, so I need my activation energy, E of A, is probably very high. Okay. All right, looking at the next one down here. On this one, it says, consider the reaction this. Now it's actually given you the concentrations. Well, all you have to do is set up your KEQ. Remember, it is products over reactants. I have a lot of kids get that messed up, and they flip it, and then everything's wrong. So products on top, reactants on the bottom. Because I'm always worried about my products, how much can I make as a person that's trying to make money, right? So that's how I remembered. Products on top, reactants on the bottom. Okay, so I'm putting that in, NO squared divided by N2 times O2. Make sure it's times. Then you just plug in.
Why
Yes.
is it squared?
The squared came from that 2 in front. So any coefficient becomes the exponent. Okay? You're putting it in. Make sure you square it. When you hit the divide, make sure that whole thing on the bottom is in parentheses. Yes?
Now, when you're plugging in numbers, do you take the AMU and plug it into the
No. I'm not using AMU. I'm using concentrations.
Okay, great.
Okay? Now, we used to not have that little fun button that is the parentheses, so I have learned just to do this times this, hit my 1 over x button, and then times it by this squared. Okay, however you want to do it, make sure you double check it. That's a big one. Make sure you double check your numbers on the test, because you'll have every possible wrong answer you could get. Okay? All right, number 17. Consider the combustion reaction. Again, this tells me it's going to be on the product side that I'm adding 531 kilocalories. So it's just like it's in my reaction. And because it's in my reaction, I can make a ratio. So I start with the kilocalories they gave me, and then I say divided by the kilocalories, and it wants 1 mole of propane. Well, I know that's oxygen, CO2, water, so this has to be the propane. I put 1 mole of propane on the top. This divided by 531, and I get 182 moles of propane. That's a lot. Any questions on how to do that? Okay, make sure you're staying with me, and if you have questions, ask me. Are we okay? Go forward. All right, next one. So this has to do with our lab that I had you do that was not official because I wanted you to remember it. What things can I change to increase the rate of reaction? I can change the temperature. I can change the concentration. I can change the pressure. I can change the particle size. And these two actually were the same. I'm going to change this to particle size. Because the vessel size will determine the pressure, right? So if I decrease the vessel size or decrease the volume, that increases the pressure. Okay? And then add a catalyst. This is also that little movie that I showed you about the school. Remember that? The TED Talk? About the school making things react faster. Okay? So I did those on purpose to help you remember that. Okay? All right, so define a catalyst. That's the matchmaker. They're not used up in the reaction, but they increase reaction rate.
Wait, you decrease particle size to increase reaction rate.
So, whoops, sorry. Yes, decrease. Particle size down. Thanks, sorry. All right, activation energy is explain what it does. It lowers the activation energy, therefore usually increasing reaction rate. Okay? I'm trying to keep it so those of you that in the back, I know you're having a hard time seeing your own heads. Put it towards the top. Okay, then we come up to another one where we're working with our calories thing again. Okay? This is really easy if you know this. Okay? So it says walking briskly burns off about this many calories per hour. How long would you have to burn? How long would you have to, and I didn't finish this right, so we're going to finish it together, to obtain, burn off basically a candy bar that had 10 grams of protein, 15 grams of fat, and this many grams of carbohydrates. So I just took the 10 times 4, 15 times 9, because that was my fat, 46 times 4. Those are my proteins and my carbohydrates. This is how many calories. Now, I didn't finish this really good because I didn't do the next part, which is I have 359 calories, and this is a capital C. Okay? And I think that
Can you explain the capital C or lowercase c again?
capital C is kilocalorie, and I think I've just done this. I just found calories, which is a lowercase c. Let me double check. I don't think I have the book here. Dang it. Okay, so I'm going to bring up your book online. But basically, we're just going to take this and we're going to say, I'm just going to use it as calories, lowercase. But if it was capital, we'd have to just change it to kilocalories. That's the difference. Okay, I need 280 calories. That's how many I burn in 1 hour. So then I just divide that, and I'd find out how many hours I would have to walk at that brisk pace to get rid of that candy bar I ate.
What was on that sticky note?
Well, this is here, but I'm not sure if that's capital C or lowercase c. That's what I'm saying. This, I don't know, because if it's capital C, that's 2.8 times 10 to the 6 calories, and that's going to take a lot more time to burn off.
Just a lot.
Okay? Does everybody understand what I'm trying to figure out here? Yes.
So is that for right there 4 if it was the kilocalorie?
This would be if these were kilocalories. And let me see if I've got, I left the other book home, and I think, let's see if this other book has it. If you've got access to your book online, it's on chapter 6.
Is there an airdrop on it?
Want to be as a no.
Just real quick. If this doesn't work, I'll look real quick on your book. But I want to make sure we get through all of them.
This is my partially on.
This one does not have it. Okay, I will look that up at the end when we go back. We'll come back to that one. Okay? All right, so let's go forward. I'll just put a star by this one, and I'll come back to it at the end of the video and tell you if it's low or high. Okay, you'll be given a graph like this. It will have numbers on the side. I forgot to put units, so I'm going to just assume it's kilojoules. You just need to be able to read stuff off the graph. Okay, so my reactants are here. My products are here. My activated complex is here.
Wait. Where in the world is that?
My E of A is here. My delta H is here. Now, if I know all of that, reactants, products, activated complex.
Wait, how did you know
How did what?
How did you know the E of A was on that line? Isn't it on the top?
Reactants to the top of the curve. That's E of A. Okay, so what is the activation energy? So I go from here, which is 5, all the way to 20. So the difference is 15. Okay, so I'm just reading the numbers.
What does E of A mean?
Activation energy. Okay, what is the energy of the reactant? So I come over here and I look, and the potential energy of the reactants is 5 kilojoules. I'm just reading off the chart. What is it? What is the energy of the products? Again, just reading off the chart. What is it? But I need to know where they are. And then what is the difference? What is delta H? Since my products are over my reactants, it's going to be a positive. And yes, on delta H, you have to write the positive or the negative. So it's a positive change from 10 to 5. So I have to add 5 in to get up from 5 to 10. And then the energy, is the reaction exothermic or endothermic? I have to put energy in, so it's endothermic. Yes?
I don't get the the 15 kilojoules.
So it started, I went from 5, that's where I started. I went up to 20, so I just take 20 minus 5 to get 15.
Okay, that makes sense.
Okay, so it's just this distance from my reactants to the top of the curve. How much was it? Yes.
So you said that it's kilojoules. We just have like the graph will be labeled, right? So
The graph will be labeled. I just didn't finish labeling it.
So
Yeah, you'll know. It could be calories. It's usually either calories or kilojoules. Okay, next step. Okay, the rusting of iron is described as this reaction right here. Okay, the formation on rust of an exposed piece of iron typically takes several months. So that tells me, is it fast, slow, very slow? Yeah, it's pretty slow. What can be said about the activation energy? It's going to take a little bit of energy to make it go, right? It's not instant. It's not going to go over that hump fast. So I put medium high. Reaction rate, slow. It's not extremely slow. It doesn't take years and years, but it doesn't happen in a matter of seconds. So it's slow. Okay, next one. The rate of the chemical reaction increases with an increase in concentration of one or more of the reactants because, yes,
can
ma'am.
you go over the activation energy, how you decide whether it's
So because it took several months, that means I've got to come up this hill. It's going to take time to climb that hill. I've got to have a big climb. If it didn't take several months, I'd probably have a smaller hill to climb. Right?
So the activation energy is how big that hill is.
Yeah.
Because that's like the EA.
And then because of that activation energy, that determines how fast my reaction can go. Because if I need a lot of energy,
Then it takes a long time.
yeah. Okay, so the next part here, the rate of reaction increases with an increased concentration of one or more of the reactants. Because, well, think about, I think I told you about Lima, Montana, graduating class of 3 to 5, depending on the year. And then our graduating class. Chance of you finding the one in Lima, Montana, probably low, right? But if you increase the amount of people, amount of girls, amount of boys, that's like increasing the reactants. The chance that somebody can find somebody at Northridge in the graduating class is higher than it is at Lima, Montana. Okay, because of that, more reactions, there's more chances for collisions, more chances of going out on a date than if there are 4 guys and 1 girl in Lima, Montana, right? Graduating, where you have 300, 400 of each down here, okay? Because of that, more shift, therefore, more shift to the products. I should have put products here. So it will shift from the reactants to the products because I'm now taking 2 things and more chance of it going forward and making a couple, right? So this would be A and B, and all of a sudden I'm a couple, AB, because I had a chance to collide, a chance to interact, okay, within the same school. All right, so then we get another activated complex. Can you see how many activated complexes you're seeing in this? You're seeing that many on the test. The review is a mirror image of what the test is. So whatever you see a lot of on here, you'll see a lot of on the test. Label the following. So instead of labeling the following, she'll have A, B, C, D, E, something like that. And then she'll have you match what's what. Okay? So just remember, reactants are where you start, products are where you end, right? Activated complex is when you're at that top of the hill and you can go either way. E of A is always from the reactants to the top of the curve. Delta H is from the reactants to the products, wherever they are. Here, we're going to lose energy because the products are lower. So what kind of reaction graph is this? Exothermic, yes.
So you said delta H is reactants to products?
Reactants to products, whatever that is, that's your delta H. Here it's below, products are below because it's below, it's given off, exited. Heat is energy is electric.
If the products was above the reactants, it would be delta H positive?
Yes.
Do I have to, you'd have to write the positive sign out?
Yep. Okay, so you need to be able to label this. Pretty easy if you know, again, easy points. Don't have to do a lot of mental work. Would I put this on my thing if I didn't know? Yeah, I would put this on my thing. Okay, so next thing is classify. So again, I labeled all these as practice. Here I've got a negative delta H. Here I've got a positive delta H. This one is endothermic because I'm putting energy in to end up higher. This one is exothermic because I'm taking energy out to end up lower. But everything else, reactants to activated complex is E of A. Reactants to products is delta H. So you should be able to label these pretty easy. I'm hoping. Okay? We okay to move forward? Yes, you may.
This will be online.
This will be online. I'm recording it right now, and you can go forward and listen to my explanation. Go backward and listen to my explanation. I've even got the one from last year still up there. Okay? All right, we okay?
Yeah, there's no.
You go forward? All right. So on the next one here, consider the reaction, blue, where delta H is this. Negative tells me what? What does negative tell me, guys?
It's exothermic.
Exothermic. I'm hearing a lot of chatter going around that's not chemistry related. So let's make sure we're paying attention so we can do well on this test. So it's exothermic. That means I'm adding it in basically on this side, the product side. Okay? What type of reaction is this? Remember our types of reactions: single displacement, double displacement, combustion, synthesis, decomposition. This one is making CO2 and water with oxygen on the reactive side. It is a combustion. Kaboom! Okay? Anytime you're taking a carbon compound, adding oxygen, getting carbon dioxide and water, you've got combustion. Where are the bonds stronger, the reactants or the products? Well, if I'm giving off this much energy in the products, that was part of the bonds in my reactants. So my reactants had more energy. Okay? Will this reaction give off heat or take it in? It will give it off because I got that in my products. Right? Does everybody understand? If this was a positive instead of a negative, I would put it in the reactant side, meaning my products would have more energy in their bonds than my reactants because I had to add in energy. Okay? All right, then guess what? It's Lechatleir again. Guess what? There's a lot of Lechatleir on there because she wants to make sure you understand it. So, again, removing, I would write this arrow thing down because you're probably going to see it over and over again. And I would do. If I'm removing and I'm putting a hole here, that means I've got to cross it this way. That means it's going backwards towards the reactants. Okay? Then I go to the next one. If I'm removing O2, again, forward towards the reactants. Removing NO, forward towards the products.
So basically, as long as it crosses that.
It's got to cross the arrow. Okay? If I'm adding, that means my arrow's got to go forward across. So because of that, it's going towards the products. Okay, adding O2, moving this over, adding O2. Again, it's got to go forward across the arrow, so it's going towards the products. When I'm making a pile, by putting it on top, I've got to spread that pile out. Okay, adding NO. Putting a pile here, I'm going to spread it out by going backwards towards the reactants. Now, here we've got to look and say, okay, pressure, I've got to look at moles. I've got 1, 2 moles on this side. Everybody see the 1, 2? And I've got 2 on this side. It's the same. Because it's the same, increasing the pressure or decreasing the pressure will not change the reaction. It'll stay the same. Because the pressure on both, it has 2, it has 2. Doesn't help me to move either way. Okay? That might be something she does to you. Okay? So make sure you're aware of it. It can do that. It can do no change. All right, this one down here, again, another Lechatleir. Gee, I wonder how many Lechatleirs are going to be on the test. Yeah. Okay, so again, before I even go, I'm going to say, okay, I've got 2 moles of gas on this side. I've got 1 mole of gas on this side. So if I hit pressure, I know what to do. Now, if it had heat, remember, you treat heat just like you do any other thing. You put it in, and if it was a negative like this, I would put it in on this side. And then when I added heat, I'd go on top. If I took it away, I'd put it on the bottom. Same thing, right, as any other chemical. Okay, so down here. Yes, ma'am?
Can you go over what you do when it's removing again?
Removing, you put the arrow down underneath, and you have to cross the main arrow here to get to it.
Okay.
So you fill the hole. Okay? All right, so here we go. If we're removing CO, Whoops, sorry, too high. Removing CO. I've made a hole here. I've got to fill it. I've got to come this way to fill it. Okay, so it fills the hole. So I'm going towards the reactants. Yes. Yes. Removing Cl2. Removing Cl2. Going towards the reactants. Okay, guys, you should be writing this down or staying with me, not playing footsies or whatever with your friends. Okay? Removing COCl2. Again, making a hole here, trying to fill the hole by moving things over from the other side. So I'm moving it this way. So I'm going towards my products. Now we're going to go through adding. So if I'm adding CO, it's going to go away from that pile so I can help spread it out towards the products. Same thing happens when I add Cl2. It's going to go away towards the products. Now, if I take and erase those so they're not in the way, if I add COCl2, it's actually going to go away from that, which makes it go towards the reactants. Now we go back to where we were looking at our gases. We have 2 on this side. We have 1 on this side. If I increase the pressure, it will go to the side that has the least number of gases, which happens to be the product side. So I'm going to go forward to the products. If I decrease the pressure, now, increasing the pressure, that she could also say decreasing what? Volume. Because if I decrease the volume, I increase the pressure. Here, instead of saying decrease the pressure, she could say increase the volume. Right? If I decrease the pressure or increase the volume, I'm going to go to the side that has the most moles, which happens to be my reactants. Yes? So you have 1 mole here, so you're looking at the coefficients. 1 here, you have 1 plus 1 gives me 2. Okay? All right, we okay with this? Again, these should be easy points. These should be easy points. They're not heavy calculations. Yes, sir?
Wait, how come if they're so easy, why is there so much on the test?
Because so many kids screw them up.
Oh, so she's not being nice, she's just trying to get us to screw up.
So this test we should do good on.
You dang well better do good on. Okay, I will try for you. Okay, so let's do it again. Guess what? We see another Lechatleir.
Okay, so
Right?
I'm actually getting this one.
Okay, so we're looking at the numbers in front. We've got a 1 here. Be careful. Okay? What is wrong with what I did here? I did it on purpose because this is what some kids often do. What did I do wrong here? Show me what I did wrong.
There's a 1 on the bottom, so I'm going to change the time.
You zoom in here. What does pressure affect? Gases. What did I include in my number of moles?
Aqueous.
That is the biggest mistake I see. So how many moles do I actually have on this side? 6 moles of gas. How many on this side? 6. Guess what? They're the same. So when I get down here, where I screwed up, is it going to move? No. It's going to be no change. She loves to do that. No change, because I have the same number of gas moles on both sides. Okay?
Wait, I thought it was 6 and 12.
Ah, look at this. Okay, this is liquid. Doesn't count. This is aqueous. That doesn't count. The only thing left are the 2 moles of gas. One has 6 on this side, one has 6 on this side. So I have 6 moles of gas on both sides. Yes?
So the 6, 12, and 6, like for the CHL part up there, doesn't count because it's not
Because it's aqueous.
So
So when I'm doing gases, when I'm worried about pressure, it doesn't count.
So if it was grams, would it be 3, or would you do like the 6 times 12 times 6?
6
Like
times 12 times.
metaphorically saying, if it was grams, would it just be 1 or like 3?
Okay, I'm confusing why you're bringing grams in.
Like, so metaphorically saying, if that was like grams
this
instead
was
of aqueous.
Gas, you mean?
Yeah, that's right. That's better.
I was
If
like,
it was gas,
If it was gas, then I would include it. But if
So
it
then
since
would it
it's
be
not,
3?
so it would be 7 on this side.
Okay,
Because this would be 1
so
and
that's only
6.
1. So you don't include like each of them.
No, you just look at the number in front, the coefficient. Okay, good question. Okay, I was trying to figure out where you were getting
Gas.
grams. It's gas. Okay.
Not grams.
Yes.
Wait, so how come you can do the Lechatleir? Sorry, I don't know the name, but like
Lechatleir.
yeah, how come you can do that for the reactants and products thing, but not for the increasing and decreasing pressure?
I'm still doing it for the increasing and decreasing pressure, but on this one, the moles of gas on both sides are the same. Because they're the same, it won't change. One's got to be bigger or smaller than the other in order for it to change. Okay, so let's go back and do, I'm going to zoom back out again. Let's do this removing this. So I'm going to now remove this. I got to force it towards it. So when you're talking about Lechatleir moving forward and backwards, it's where I'm putting things in and putting things out. Increasing pressure and decreasing pressure, I'm not putting things in and out. I'm just increasing the pressure on it. Okay? Sort of like finals does to all the students. It increases the pressure. Okay? Okay, so here we're removing. We're going to go backwards, so we're going to head towards the reactants. Okay, so if I remove now, if I remove O2, again, I've got to cross that arrow, so I've got to fill that hole, so it's going to go back towards the reactants. Remember, you've always got to go over the arrow. Wherever you are, you've got to go over the arrow. If it's pulling it out, you're filling the hole, going towards it. If you're putting it in, it's going away from it. So removing CO2, again, filling the hole, going towards it. It's going to go towards the products. Removing H2O, it's going to go towards the products. Okay, I'm going to erase some of this because it's getting a little cumbersome. Just don't want to erase those because I don't want you thinking about that. Okay, adding this, I'm going to go across. I've got to spread it out. It's going to go across the arrow this way, so towards my products. Adding, again, making a pile on this side. It's got to cross the arrow, going to the products. Adding on the product side is going to force it to the reactant. So when I do these bottom two, when I add here, force to my products, or my reactants, add here, force to my reactant. Okay, do we have any questions with this? You can see there's a lot of points here. As long as you've got it straight in your head, you're going to do well. Yes?
So on the test, would she just show us the equation and then just like, let's say B, and then you would just say reactant or product?
She'll say, which way will the reaction shift? Towards the reactants, towards the products. Okay? All right, next part here. So a manufacturing company, let me get up here. Manufacturing company requires 98 kilojoules of energy. That's not really a lot. Okay? Of energy to power one of its machines for a day. The reaction shown below would be able to provide, would the reaction below, it should have said, be able to provide a sufficient amount of energy for this purpose. Explain why or why not. So this is basically what's happening in a mercury battery. So you ended up with this. What does that say? Oh, and actually I've done this wrong. Should be no. Why? What is this? It's a positive, right? What is a positive? That means I've got to put it in on this side. So I got 182 going on that side. It doesn't give, it needs 182 kilojoules. I want it to give off 182 kilojoules. I don't want to take 182. Because it takes that much, this machine needs, not only, it needs this much, and this equation needs that much, so it doesn't give any. It takes. So this would not be a good energy equation to be able to use to power that machine, because that needs energy. This is what happens when you do stuff when you're watching TV.
I'm surprised that it's done. You watch it, that's the thing done.
Netflix.
What show?
That was a medical response one. I don't remember.
This is how
I'll pass it back. Okay, so this next part has to go back to our little thing right here. Again, if you don't know this, write it down on your card. Because all you have to do is look at a list of stuff and determine what has the largest and which has the smallest amount of calories. Okay, so if you know this conversion, all you have to do is go, oh, that's fat, times it by 9, I got the calories. Oh, that's carbohydrates and protein, times each of them by 4, I got the calories. Protein times it by 4, I got the calories. Carbohydrates times it by 4, I got the calories. Fat times by 9, protein times by 4, I got the calories. Yes?
How do you know whether it's a big C or a lowercase c?
That's what I'm gonna have to go back and look.
It's a big C.
I put a big C here, so I'm thinking these might be big C's. Okay? All right. Any questions on this one? Do we understand how to do it? So the answer is no, because this was a positive, so it's going to go on the reactant side. So it's not going to give up energy, it's going to require energy. That's the thing there. Okay, we okay? Trying to make it through all of it before the end of the period, so everybody has a chance to see all the review. Okay, again, this will be posted up on Davis' site, and I guess I'll post it on Weaver.
Will the video
Maybe.
be posted or?
What?
Will the video be posted?
Yes, video. Yes.
Will it also
Oh.
audio?
Yeah, 'cause the last
I'm
video was
hoping
audio.
so, because it's showing me right here. You see the green? That's me talking. It's showing that I'm talking, so I'm hoping it will.
So is it gonna hear us in the back?
Oh wait.
Probably.
Yes, say whatever you want.
Okay, so let's go on this next one right here. Which term correctly describes a reaction in which the energy of the products, this is again activation energy. If you've got this, you've got it, is higher than the reactants. That means I end up like this. That's endothermic. Which is lower. Means I'm going to go like this. Exothermic. That's all that is. Okay. If we have an equilibrium constant with a value listed below, which is favored? The reactants to the products. Remember, bigger than 1, products. Less than 1, reactants. Equal to 1, neither. So very quick and easy. Oops, except I missed there. This is what happens when you don't have your glasses on when you're doing that. That should be reactants because it's a negative.
Like bigger than 1.
So KEQ is bigger than 1. It goes to products. KQ less than 1 goes to the reactants. And you can tell site-wise I didn't see that negative when I did it at home. This reaction would be a lot faster, more forward than this one, but still the products are favored. Okay, then it asks, which K value below is consistent with an equilibrium system in which neither the products nor the reactants are favored? K equals 1, KQ equals 1 only, that's it. Okay, for an exothermic reaction, increase the temperature, increases the rate of the, because exothermic, where's the heat? A plus B yields C. Exothermic means I also have heat on this side, right? So if you have to write yourself a thing down, where's the heat? Exothermic, the heat's on the product side. So if I increase the heat, it's going to go away from the heat, which means I'm going to have more of the reactant. So increases the temperature, increases the rate of the reverse reaction, makes it go more backwards. For an endothermic, that means I'm going to have heat on the reactant side. Heat plus something yields, blah, blah, blah. If I increase the heat on the reactant side, it's going to force the forward reaction, makes it go forward, right? Because I'm going to put a pile here, it's going to go forward. Okay, then we got another with KQ. You get it right, the KQ. Remember products over reactants You can sort of see what the theme of this whole thing is. If you know 3 basic things, the activation energy, Lechatleir, and how to do a KEQ, you basically got them all. Okay, so you write the KEQ. There's ones in front of all of these, so I just go products divided by reactants, plug in the numbers they gave me in the right place. Please double check, because that's one of my boo-boos right here, is I almost put it in the wrong place. Yes, sir.
Will she give you the values of the moles?
Yes. If she wants you to solve the KEQ, she has to. Okay, so she's going to plug that in, and you'll get the value of K. Okay, what can I tell about this reaction? What does it favor? Yeah, the reactants are favored.
How do we know?
Because it's less than 1. So it's more of this and a little bit of this. Okay. Next one, a reversible reaction that has reached equilibrium when what conditions are established? The forward and the reverse reaction rates are equal. The forward and reverse reaction rates are equal. Okay. This is sort of a random question. I thought it was really weird that she put in something like this. But what are the 3 elements used in catalytic converters? Rhodium, platinum, and palladium.
So if we just write that on our card.
Okay. The reason why most catalytic converters are stolen is because of platinum. Platinum is expensive. So they recover that and leave the catalytic converter.
What is a catalytic converter?
It takes in, it's in your car, and it actually takes the leftover gasoline and converts it to used.
Oh, is that why cars are expensive?
It can also convert the COs that come out to CO2.
What's that last one?
What's what last one?
The very last one.
Palladium. Okay, next one. Whew, 39. In the reaction, blah, 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 blah. Got that? The K values is many thousands above 1. So it doesn't give me the K value, but it tells me many thousands above 1. This leads to knowing that at equilibrium, there will be more products than reactants. That's it. Done.
Oh. Okay, so
KQ is greater than 1. More products than reactants. Okay. Next one here, we've got this lovely equation here with carbon monoxide and chlorine given as carbon monoxide chloride, which is actually, yeah, anyway. And it has a negative delta H. Before I go in anywhere, what does that tell me? What does a negative delta H tell me?
Oh, it's less than 1. It's exothermic.
It's exothermic. It tells me that that heat should be on this side. I don't really need to know where the heat is, or what the heat is, but I need to know where it is. I can put that number in later where heat is if I want to. Okay, so when the temperature of the vessel is increased, so that's like saying I'm putting heat here. I'm making a pile here. It's going to force it that way through the arrow, right? So shift it towards the reactants. So this is exothermic because the heat went on the product side because it's negative.
what was the one before? Okay, thank you.
When the temperature of the reaction is decreasing, that's like taking this arrow and shifting it down below, creating a hole. And so the reaction will shift to try and fill the hole. So it'll shift towards the product. Same thing we've been talking about. We're just talking about just the heat. But that's where you get it, is that delta H. And that negative tells you it's on the product side. If it's a positive, put it on the reactant side. Okay? Now, you've got a reversible reaction here. And that means this should be like that. I forgot the arrow, sorry. So, where the K is this, very, very small. Can the molarity be determined from this information? Well, basically, I can write the KEQ, which would be concentration of PCl5 divided by the concentration of PCl3 times the concentration of Cl2 and I know it's equal to 0.5, but I don't know what these numbers are. The brackets are the concentration. So I can't determine the exact molarity, but I could give the ratio. I could put in X for each of these and solve for it, but that's not going to give me the molarity. Okay, so be careful. Again, you're given an equation here, and you're asked to write the expression. Remember, it's products that are on the top over reactants on the bottom. So the first thing you do is start writing like this. Remember, the exponents are the coefficients. Okay, then I take the bottom and make it my reactants. And then I look for my reactants over here. There's only one that says 4NO. Only one. I've got it. Okay, so don't look at the answers until you've written your own equation, because then it's very easy to not be messed up by it. Does that make sense? Yes.
So that equation you just like solve.
So I just put it. There's my products. There's a 4 NH3,
Oh, so you just wrote
5
it out.
O2.
So you like
4
basically
NO.
reverse it. That's what it was, and then you do the whole like.
So my products are on top, my reactants are on the bottom, so I can write the equation. Write the equation before you look at her equations. Okay, and you'll get it right. Okay, next one. The value which would be the slowest and the fastest reaction. So remember, E of A is the distance from a reactant to the top of the curve. That's my E of A. So if my E of A is large, it's going to be harder to get over than my E of A being small. So if it's small, it's probably going to be my fastest reaction. If it's large, it's going to be my slowest because it's going to take more energy to get over. Does this make sense? Okay. Last one here on the bottom. Consider the reaction this, where we've got a negative again, so I'm adding that to my product side. So it has become part of the equation. Because it's becoming part of the equation, when I get to my mole ratio, I can put that in as a mole ratio. So I start with my 292 grams of NO2. The first thing I need to do is add up NO2. So if I add up NO2, I've done it right here. That's how many grams are equal to 1 mole. Put the grams on the bottom, 1 mole on top. Then I come to the equation. Here's the 3, and there's my number of kilojoules. So 3 moles on the bottom, kilojoules on the top, and I get this many kilojoules. And it already told me it was released, but I could put the negative there, because it is negative, to tell me that many is being released. Okay? Okay. I was trying to scoot it up a little bit, sorry. I'm seeing the bob and weave at the back, so when I see the bob and weave, I know I'm not high enough. How are we doing so far? How are we feeling? Confident? Okay, hopefully you'll ace this test. It's really not that hard. Shoot for acing, man. Shoot for acing. We okay to go forward? Last page. Whew, just got enough time. Okay, consider the combustion reaction. Again, put it into the equation. The negative tells me what? Exothermic, so it's on the product side. So I put it over here. 531 kilocalories. Okay? I know I've been given kilocalories. They want grams, so I'm going to add that mass up real fast. So from the periodic table, 3 times carbon's mass plus 8 times hydrogen's mass. I get my mass. That's equal to 1 mole. Okay? So I'm going to take this, kilocalories. I'm going to use the equation first because that has kilocalories and it's 1 mole. So I'm going to put the kilocalories on the bottom, 1 mole on the top. Then use my added up, 1 mole propane to the 44.097 grams of propane. Kilocalorie, mole, I'm left with grams. Times it through, divide by 531, and I end up with this many grams. Okay, so it's just stoichiometry. Stoichiometry. Any questions on this one? We okay? All right, the next one is like unto it. It's actually the same exact equation. So we're still plus 531 kcal, right? It's still exothermic, which I'm grateful you guys saw that. How much heat is released? So I'm looking for kcals. When I use that many molecules of O2 burned. So because I'm in molecules, remember I have to get to moles before I can use the equation. So I'm going to use Avogadro's number. If you do not have it saved as alpha A in your calculator, make sure you put that whole thing on the bottom in parentheses. I would do that anyway because you have a 5 here. So you've got molecules. You're going from molecules to moles. Then you're going to the equation. You are burning that much oxygen. So you're going to use this 2 kcals. So you're using the 5 and the kcals. You want to get rid of the 5 moles of O2. You want to go to kcals. So times it through, divide, parentheses, times to the bottom. You should end up with this many kilocalories, which is not a lot. But if you look at that, that's less than a mole of oxygen, right? So we don't have very much oxygen. Less than 15, 16 grams. Moving that up. Okay, breaking a chemical bond takes energy. You have to take energy to break a bond. Forming chemical bonds actually releases energy. And then the distance between the reactants and the top of the curve, remember, is known as the E of A, activation energy. Okay, it goes from there to the top of the curve. And then just remember again the bottom here, high E of A's generally are slow reactions because they've got a very high hill decline, right? Low E of A's are fast because they've got a very low hill decline. Okay, let me look real quickly and see if we can find that. I think it's kilocalories. Let me double check. I'm going to your book in chapter 6.
What's this?
I wrote it down. Something else on the PowerPoint instead of having all the pictures.
Can you guys reach the book? I cannot get to the book online. Yes. I will be here today after school and tomorrow after school, yes.
Well, I guess they
I like plan ideas, I like because I'm so stressed.
And then
Sorry, it's going really slow.
To complete your
Why did I do anything else? I went to my Spanish teacher. I didn't know I had to do so much to make up my Spanish. So like, and she's like, I was like, there was like pages.
Okay, it's kilocalories, guys. It's right here.
Do you guys want to treats? Is it just give us like?
It's not showing up very good, but it's right here.
So that's the capital C.
Capital C.
Capital C is the same as kilo, is writing like kcal.
Capital C is same as writing kcal. Okay, so in here in your book here, it's 449 for kcal, and it's 4,000, 4,000, 9,000 for calories. The 449, and it's kcals. Make sure you got that written down. So it is this one. It is. Should be a capital.
So if it's the lowercase, like when it says the lowercase c, then should we use the lowercase c one?
You can, or just divide it by 1,000. Give it
How
kcals.
likely is it that she's going to use that to confuse us on the test?
I don't. I think she's this. I think she's this.
Can I take a picture of that sticky note?
Yep.